so that we can assure you top-notch grades in your exams. Okay, so let's begin with the topic directly without wasting much time. So, introducing you with carbohydrates. Firstly, what are carbohydrates? So, by definition, they are hydrates of carbon. Okay, now when I say hydrates of carbon, carbohydrates, it is self-explanatory. So, hydrates, when we saying they're hydrates, then you understand that they must be having hydrogen and oxygen. Then they are hydrates of what? Carbon. So they'll have carbon as well in their structure. So they are composed of hydrogen, oxygen, and carbon. Then the general formula is CnH2O whole N. Okay. So this is for monosaccharides. Okay. Then they are aldehyde or ketone derivatives of polyhydroxy alcohol. So polyhydroxy, as the name suggests, poly means many and hydroxy is alcohol, OH group, hydroxyl group. So any compound that has hydroxyl group, it becomes alcohol. Now there must be multiple hydroxyl groups. Okay, so polyhydroxy, those alcohols which have more than one hydroxyl group. So they're aldehydic or ketonic derivatives. They form your carbohydrates. Okay. Let's understand this via glycerol. So this glycerol here, as you can see, it has 1, 2, and 3. 3 hydroxyl groups. So it fulfills this condition of polyhydroxy. Okay. So it has polyhydroxy alcohol, your glyceride. Now its aldehyde derivative is glyceraldehyde and its ketone derivative is dihydroxyacetone. Now you can see in glyceraldehyde, this aldehyde group is present here. Okay, so this hydroxyl has been replaced by this aldehyde group. So the aldehydic derivative of this glycerol is your glyceraldehyde. And here you can see in dihydroxyacetone, you can see this ketone group. Okay. So the ketonic derivative of glycerol, it is your dihydroxyacetone. Okay, so these are the simplest carbohydrates. So glyceraldehyde and dihydroxyacetone, they are the simplest carbohydrates. Okay, now this glyceraldehyde, it is also considered as the parent carbohydrate. Now, this functional group in the aldehydic derivative is at position 1. So, it has first position. But in dihydroxyacetone, you can see this ketone functional group, it is at second position. Okay. So that was briefly about introducing you to the simplest carbohydrates. Now, moving on to the classification of carbohydrates. So, they are classified into monosaccharide, disaccharide, oligosaccharide, and polysaccharide, depending upon the number of monomeric units. So, monosaccharides, they have single sugar unit. So, they are monosaccharides. Now, disaccharides, they have two monomers. Okay, so two sugar units when joined together via a glycosidic bond, they form disaccharides. Now, oligosaccharides, they have 3 to 10 sugar units. And polysaccharides, they are those carbohydrates that have more than 10 sugar units. They form your polysaccharides. Now, monosaccharides, depending upon the number of carbon atoms, they can be, if they have three carbon atoms, they can be called hexoses. If they have five carbon, they are known as pentoses. If they have six carbon, they are known as hexoses, and so on. Most important are the hexoses. So we've studied the metabolism basically of hexoses only. Now you see what we were studying, those cycles. Now you get it, glucose and all that. So they are your hexoses. It is an aldohexose. Now, also your monosaccharides, depending upon the functional group, they can be classified as aldoses and ketoses. So based on the number of carbon atoms, if they have 3 carbon, 4 carbon, 5 carbon, they are trioses, tetroses, pentoses, hexoses. And depending upon the functional group, if they have aldehyde functional group, they are known as aldoses. And if they have ketone functional group, they are known as ketoses. So your glyceraldehyde, it has 3 carbons. We've just seen in the first slide, and it has an aldehyde functional group. So it is an aldose. And your ketose is 3 carbon triose ketose, that is dihydroxyacetone. So it has 3 carbon, but when the functional group is ketone, that is C double bond O, then it is your ketose dihydroxyacetone phosphate. So what is the difference? Both glyceraldehyde and your dihydroxyacetone, both of them are trioses. They have 3 carbon. They are 3 carbon monosaccharides, but the difference is in the functional group. That is, your glyceraldehyde, it has aldehyde functional group, and your dihydroxyacetone, it has ketone functional group. Now your tetrose, that is 4 carbon. So they are erythrose and erythrulose. So erythrose is the one which has aldehyde functional group, and erythrulose, it has ketone functional group. Similarly, you have pentose. So the 5 carbon aldose is your ribose and xylose and arabinose. And your ketoses for 5 carbon, they are your ribulose, xylulose, and ribulose. Then the most important, hexoses. So they are your glucose, galactose, and mannose. And your ketohexose is your fructose. So your fructose is your ketohexose. And your glucose, galactose, mannose, they are your aldohexose. Okay. Now moving forward to disaccharides. Now disaccharides, they are formed by joining 2 monosaccharides by glycosidic bond. Your glycosidic bond is a covalent bond. Now so when 2 monosaccharide units, they are joined together via a glycosidic bond. That is the bond which joins 2 monosaccharide, that is known as glycosidic bond. What is formed? A disaccharide is formed. Now your disaccharides, they can be classified into reducing disaccharide and non-reducing disaccharide, and this is a very hot question in your vivas, okay, during your table vivas. What are reducing disaccharides and what are non-reducing disaccharides? This is very disaccharide. It is mal by reducing disaccharides and non-reducing disaccharides. Yeah. So I think the connection was lost. I'll begin with disaccharides again. So your disaccharides, they are formed by joining 2 monosaccharides together via a glycosidic bond. which is a covalent bond. So when two monosaccharides are joined together, they form a disaccharide unit. Now this disaccharide unit, it can be a reducing disaccharide or a non-reducing disaccharide. This reducing and non-reducing disaccharides, they are very important for your practicals, for your table vivas. You very frequently get asked about the difference between or what are reducing and non-reducing disaccharides. So the examples of reducing disaccharide, it is maltose, isomaltose, and lactose, lactulose. And non-reducing disaccharides, it is sucrose and trihalose. Now, what is the concept? What do you mean by reducing and non-reducing disaccharides? So you're reducing disaccharides in this, at least there is one free functional group. So when there's one free functional group, it is able to get involved in other reactions, and therefore it is what is known as reducing disaccharides. So you're reducing disaccharides, they have at least one free functional group. And what are non-reducing disaccharides? They are those where when the two monosaccharide units, they are being joining, so the functional group, both the functional groups are engaged in the glycosidic bond. So there you do not have any free functional group. So in shortly, if you try to remember, so you're reducing disaccharides are the one which have at least one free functional group, and your non-reducing disaccharides, they have no free functional group. Now, let's understand this concept with the help of diagrams. It is very easy. Although you're not supposed to know these structures, you're not supposed to know these diagrams, but for the sake of understanding, so that you understand what do you mean by reducing and non-reducing, just mugging up that reducing have free functional group and non-reducing do not have free functional group and not understanding what it is of no use. Okay, so let's begin with the first example, that is of maltose. Now, as we said, that maltose is a disaccharide, and what are disaccharides? They are composed of two monosaccharides. So in maltose, what are those two monosaccharides? They are glucose and glucose. So in maltose, two glucoses are joined together to form maltose. Now, how are they joined? Now they are joined in alpha 1,4 glycosidic linkage. I think the connection was lost again. Okay. Now, so beginning with what are reducing and non-reducing sugars? So as we said,
Ma'am, try to share the screen now.
Yeah. Am I still logged in from the other device?
You want to log in from other device?
Wait, am I still logged in?
Yes, ma'am. It is showing two devices here.
Okay.
But still, there are intermittent issues, ma'am. Sometimes losing the connection and connecting back.
Yeah. I don't know what's wrong.
That's just because of that signal only, ma'am. Network signal only. If you have a strong network signal, then we won't face that intermittent issues, ma'am. I have stopped the recording. Then we can start once the class starts again.
Can you see my screen now?
Yes, ma'am. Just maximize the screen, ma'am. Yeah, now fine. One second, ma'am. It's still opening.
It's not in. Is my screen visible now?
No, ma'am. Now visible, ma'am.
It's
Now visible.
okay. Okay. Okay, I'll begin.
Will you start, ma'am?
Yeah, yeah.
Okay.
Okay, so the connection was lost. I'll begin with reducing sugars again. So we just discussed that your disaccharides, it is of two types, reducing and non-reducing disaccharides. Now, reducing are those which have a free functional group. See here, we said that reducing disaccharides, they are the one with at least one free functional group. And non-reducing disaccharides are those where the two monosaccharide units are joined together in such a way that both your functional groups are engaged in a glycosidic linkage. And this is very important for your vivas. This question is very important. Many a times in vivas you get asked about reducing and non-reducing sugars. So basically mugging up is will be of no use that you just mug up that reducing sugars have a free functional group and non-reducing do not. Here is a little picturesque diagram. I'll explain it to you so that you understand the concept. Although for your theory questions, it's rarely asked. So maltose, it is a disaccharide, and disaccharides, as we said, they're composed of two monosaccharides units. So in maltose, what are those two monosaccharides units? They are your glucose and glucose. So two glucoses join together to form a maltose. And how are they joined together? They are joined in alpha 1,4 glycosidic linkage. Now, what is alpha 1,4? Now, alpha here, the cyclic structure, in the cyclic structure of glucose, there are two conformations. Okay, so this cyclic structure has two conformations. One is alpha and one is beta. So depending upon the position of your OH, hydroxyl at carbon 1, it is divided into alpha and beta. So in your beta, the hydroxyl at carbon 1 is above the plane. So in beta, the hydroxyl at carbon 1 is above the plane. Later in the lecture, we will study about the cyclic structure of glucose. So you will understand this more clearly, okay? For now, just understand that in the cyclic structure, that is something like this, we'll study. So in the cyclic structure at carbon 1 here, depending upon the conformation of OH, that is whether this OH is above the plane or whether this OH is below the plane, it is given alpha and beta conformations. Okay, so that is about alpha and beta conformation. So if the two compounds that are involved in the linkage, both of them are in alpha conformation, we say it is alpha linkage, and if both of them are in beta conformation, we say it is beta linkage. So here we are saying alpha linkage. That means the glucose here, both of them, these two monosaccharides, they are in alpha conformation. Okay. Now, what are the carbons involved? They are 1, 4. So you can see this is carbon 1, carbon 2, carbon 3, 4, 5, and 6. Okay. And for the other monosaccharide unit as well, carbon 1, 2, 3, 4, 5, and 6. So now the carbon 1 combines with carbon 4 here. So this is alpha 1, 4 linkage. So and here you can see this is the free functional group. That is why we say your maltose is a reducing sugar, because here there is glycosidic bond between the two glucoses. How? Via alpha 1,4 linkage. So this carbon 1 or 1 monosaccharide of glucose is involved in a glycosidic bond with the carbon 4. This is 1, 2, 3, and 4. Carbon 4 of the other, forming an alpha 1,4 glycosidic linkage. And this here you can see this aldehyde group of the second glucose monosaccharide is free. So this is the free functional group, and since there is a free functional group, we say that maltose is a reducing disaccharide. Okay. Now moving forward to isomaltose. In isomaltose, the two glucoses, they are engaged via alpha 1,6 glycosidic linkage. So the carbon 1 of 1 monosaccharide is involved in a glycosidic bond with the carbon 6. In what was happening in maltose, it was carbon 4. In isomaltose, it is carbon 6. That's the only difference. Now in lactose, the two monosaccharides unit are galactose and glucose. Now the bond is beta 1,4 glycosidic linkage. So here it is beta because your galactose and glucose, they are in beta conformation. So it is known as beta linkage. Now the carbons that are involved is carbon 1 and carbon 4. So you can see carbon 1 and carbon 4, they are engaged in a bond forming beta 1,4 glycosidic linkage. So that is your lactose. And what is the difference between lactose and your glucose? It is the difference in the orientation of the hydroxyl at carbon 4. You can see in galactose, there is hydrogen on the right side, whereas in glucose, there is hydrogen on the left. Okay. Now, lactulose. In lactulose, your two monosaccharide units, they are galactose and fructose. And the bond is beta 1,4 glycosidic linkage. Again, if you see here in this diagram, you can see in lactose, you have a free functional group again. And therefore, it becomes a reducing disaccharide. Okay. Now, your lactulose, it is a synthetic disaccharide and it is also acts as an osmotic laxative. Therefore, it is given in liver disorders. So, this might become important for MCQs. Now, what are non-reducing disaccharides? They are sucrose. So, your sucrose, it is composed of glucose and fructose. So, the two monosaccharides of sucrose are glucose and fructose. Your sucrose is also known as cane sugar. Now, what is the glycosidic linkage? It is alpha 1 beta 2 linkage. So, your glucose is in alpha conformation and your fructose is in beta conformation, and it is alpha 1. So, here the carbon 1 is forming a bond with carbon 2. This. Now you see both the functional groups, here this functional group and here this functional group. So both the functional groups are engaged in the glycosidic linkage. So there is no free functional group. Therefore, it becomes non-reducing disaccharide. There is no free functional group as both the functional groups are involved in the glycosidic linkage. Now, trihalose, it is composed of glucose and it is alpha 1,1 linkage. So, glucose, it is a aldehyde hexose. Okay, so it has at carbon 1 the functional group. So, if the functional group is at carbon 1 and both the glucoses alpha 1 linkages are there, therefore you will have no free functional group. So, your trihalose is also a non-reducing disaccharide. Now, what are polysaccharides? Polysaccharide means that you have more than 10 carbon sugar units. So, if the monosaccharide units are more than 10, they fall under the category of polysaccharides and they are divided into homopolysaccharides and heteropolysaccharides. Homopolysaccharides are also known as homoglycan and heteropolysaccharides are known as heteroglycan. Now, by hearing to the term homopolysaccharides, I know it sounds familiar because you already have studied about glycogen in detail. So, when we were studying glycogen, I told you it is a homopolysaccharide composed of alpha D glucose. So, you have in homopolysaccharides only one type of monomer is repeating itself again and again to form the polysaccharide. So, there is only one type of monomer, that is, it is homo. Homo means same. And poly means many. So when many same saccharide is sugar units are repeated, they form homopolysaccharides, and the example of which are glycogen, starch, Kiten, cellulose, and inulin. Now, heteropolysaccharides, you have more than one type of monomer. So the repeating units are more than one. It may be 2, 3, 4. And remember, we had studied GAGs, where we had studied that it is a heteropolysaccharide. Then agarose is also an example of heteropolysaccharide, and then pectin. Now let's take up some biologically significant carbohydrates. So beginning with glycogen, the most important one, it is made up of alpha D glucose. So your alpha D glucose units are repeated to form glycogen, and we've already studied that it is a highly branched polymer, and it is the storage form of carbohydrates in animals, therefore also known as animal starch. So your glucose is stored in the form of glycogen. We've already studied that how your glucose was being converted into glycogen synthesis. We've already studied that. So it is the storage form of carbohydrate. Now the straight chain has alpha 1,4 linkages, and at branches we had studied that they have alpha 1,6 linkages. Now I think it must be very clear to understand that what is meant by alpha 1,4 and alpha 1,6. By alpha 1,4 you mean that your alpha D glucose, we already seen there are monomers of alpha D. So your glucose is in alpha conformation. Carbon is one of the first glucose monosaccharide and the carbon 4 of the second. So that is your straight chain. So the straight chain has alpha 1,4 linkage. And at branch points, what do you have? You have alpha 1,6 linkage. Now glycogen is stored at two sites. We've already studied that you have liver glycogen and muscle glycogen, and it is stored as beta particles. So it is stored as beta particles. Now, what are beta particles? They are group of glycogen. So your beta particles are group of glycogen. One beta particle has approximately 60,000 glucose residue. So one beta particle has approximately 60,000 glucose residue. So liver aggregates of beta particles, they form rosettes. Okay. So in the liver, aggregates of beta particles are known as rosettes. So you see, your glycogen is a highly branched and it is a very compact structure. So glycogen becomes a very compact structure. Here is a diagram to make it more clear to you. So you can see during the straight chain. In the straight chain, you can see this is carbon 1, this is carbon 2, 3, 4, 5, and 6. This is again carbon 1, 2, 3, 4, 5, and 6. So in the straight chain, you can see there is linkage between carbon 1 here and carbon 4 here. So this is alpha 1, 4 linkage. You can see that? And at the branch point here, they have zoomed in. You can see there is a linkage between this is carbon 4 and between carbon, this is 1, 2, 3, 4, 5, and 6. See, there's a difference between alpha, there's a linkage between alpha 1, 6. Now you will not forget this, okay? Because if you mug up alpha 1, 4, alpha 1, 6, you are bound to forget. But after having a look at this diagram, now it will stay with you, okay? It is easy for you to memorize. There is a linkage between alpha 1, 4 in the straight chain and alpha 1, 6 at branch point. Now, starch is another biologically important carbohydrate. It is the storage form of carbohydrate in plants. Okay. So, starch is a monomer of alpha D glucose, and it has two units, amylose and amylopectin. So, amylose is soluble, unbranched, and helical structure. So, it is like this. And your amylopectin is insoluble and highly branched. So your amylopectin looks something like this. So depending upon the type of plant, so in different plants, there is different percentages of amylopectin and amylose present. And cellulose, it is a major dietary fiber. It consists of beta D glucose monomers It has beta-1,4 linkage. So your humans lack the enzyme cellulase to hydrolyze the beta-1,4 linkage. Thus, humans cannot digest cellulose and therefore it is a major dietary fiber. Now you understand that why cellulose is a major dietary fiber, because in cellulose you have beta-1,4 linkage and humans lack the enzyme which can digest your or hydrolyze your beta-1,4 linkage and therefore they become major dietary fibers. So this is an important question from a point from MCQ point of views. The chitin, it is a homopolysaccharide. I'm sure you've heard of this before during your 11th and 12th standards when you must have been studying animal kingdom and structures of arthropods and all that. So it is a homopolysaccharide, forms the exoskeleton of insects. Okay, chitin is made up of N-acetyl glucosamine monomers. Now, inulin is also a homopolysaccharide. It is a polymer of beta-D-glucose. Sometimes, I've mentioned this for all because sometimes in previous year questions for your NEET PGs, you are asked that what are the monomers of the following. So therefore, it becomes important. It is used as an external agent to assess GFR. The test is known as inulin clearance test. Inulin is found in Dahlia and garlic. Now, pectin is a heteropolysaccharide. It is made up of galacturonic acid with arabinose, galactose in between, and it is considered as a dietary fiber. Now, let's talk about the ring structure of monosaccharides. So, beginning with glucose. Now, you can see this is the open chain structure of glucose. Okay, so this is the open chain structure of glucose and this aldehyde. Glucose has aldehyde as the functional group. So this aldehyde is a reactive group. Okay, so this reacts with hydroxyl at carbon 4 or carbon 5. So this aldehyde present at carbon 1, it can react with carbon 4 or with carbon 5, but majorly it is with carbon 5. To form a ring structure. It forms a ring. I'll repeat this again. So the aldehyde, it is a reactive group. So it is able to react with either with carbon 4 or carbon 5, but majorly the reaction is taking with carbon 5. So what happens? It forms a ring. So there is formation of this hybrid structure, which is known as hemiacetal. This hybrid structure known as hemiacetal is formed. So now here you can see what is happening in hemiacetal. The oxygen of aldehyde at carbon 1, it is shared between carbon 1 and 5. You can see this oxygen of aldehyde at carbon 1, it is shared between carbon 1 and carbon 5. You can see this, it is being shared. And the hydroxyl of carbon 5, it goes to carbon 1. Here you can see. So the hydroxyl at carbon 5, it goes to carbon 1. Now you can see a ring structure is formed, which is known as, it forms pyranose. And in this case, since we're talking about glucose, it is known as glucopyranose. Now you can see this is carbon 1, this is carbon 2, this is carbon 3, this is carbon 4, 5, and 6. So a glucose Glucopyranose, that is your ring structure of glucose, and 99% of glucose exists in solution state and exists in cyclic form or ring structure form. So this is basically what we found, which is found in our body or in nature. So this structure is formed, that is the cyclic structure is formed. This is glucopyranose. I hope you've understood the concept. And also based on this cyclic structure, we were talking about alpha and D conformations. Okay. So alpha and beta conformations are based on this cyclic structure only, depending upon the position of the hydroxyl, that whether it is above the plane or below the plane at carbon 1 here. Now moving forward, similarly for fructose. Now in fructose, what is happening? You can see this ketone group, and this is the hydroxyl of carbon 5. Now this oxygen is shared between the carbon 2 and the carbon 5, and the oxygen, sorry, is shared between the carbon 2 and carbon 5, and the hydroxyl is transferred to carbon 2. Now what is formed? A furanose is formed. This is a furanose. And here what was formed? A pyranose was formed. What is pyranose? Your pyranose is a, how many members are there? Count. 1, 2, 3, 4, 5. So it is a 6-membered ring which has 5 carbon and 1 oxygen. Now moving on to the oxidation of sugars. Now when a sugar, or in general when your aldehydes or ketones, they are oxidized, what is formed? Acids are formed. Okay, so when a sugar, which is, we know it has an aldehyde or a ketone group, when it is oxidized, what will be formed? An acid will be formed, which is known as sugar acid. And similarly, when a sugar is reduced, or when an aldehyde or ketone, they are reduced, what do they form? They form alcohols. So when a sugar is reduced, it forms sugar alcohol. Now when the oxidation is taking place under mild conditions, then the glucose's carbon 1 is oxidized to form gluconic acid, or the carbon 6 is oxidized to form glucuronic acid. And we know the importance of glucuronic acid, that what is its significance? It is used in the conjugation of bilirubin, and also when studied about GAGs, we had seen that it was also involved in the synthesis of GAGs and proteoglycans as well. Now, when the oxidation conditions are not mild, then both your carbon 1 and carbon 6, both of them are oxidized, and they form what? They form saccharic acid. And when galactose is oxidized, not under mild conditions, then what is formed? Mucic acid is formed. So, if we take this 1, 2, 3, 4, 5, 6, okay. So I'm not drawing all the hydroxyls and everything, but this is your glucose. Okay, now under mild conditions, when the oxidation is taking place, mild conditions of oxidation. So what is happening? If carbon 1 is oxidized, that is this one, what is formed? Gluconic acid is formed. So what will happen? Acid is formed. One, two, three, four, five, six. Okay. So this is, and this is what? Gluconic acid. And the other thing, what can happen is if carbon 6 is oxidized. So in case carbon 6 is oxidized, so here, this is the carbon. So you will have COH here. And this will be what? Your glucuronic acid. Now, reduction of sugars, if glucose is reduced by an enzyme known as aldose reductase to form sorbitol. So your sorbitol pathway or pyrrolol pathway, what is that? Pyrrolol pathway, it is the pathway that produces sorbitol in our body. So with this, we come to the end of today's class. Thanks for watching. I hope the connection is better next time. So if any queries, you can ask. Okay, thanks for watching. See you in the next class, and probably that be our last class on carbohydrates. Then we'll begin our marathon series for lipids. I hope the series is useful. If you have any queries, you can also send us later on as well.